Okay, there was an experimental demonstration, the first demonstration of this Bose-Einstein condensation, and you should learn about it. I think extremely interesting subject. It is 1995. 1995. It has to wait. It has to wait for that time. In 1995, there was Bose-Einstein condensation observed in ultra-cold, trapped, ultra-cold atomic gases. A fascinating subject, fascinating experiment. I advise you to study that. First observation was in 1995, and it was on rubidium 87 by Cornell and Wyman. And for in sodium 23 catalyst. You should read this interesting experiment. Well, since 1995, of course, there's lithium, potassium, chromium, strontium, rubidium, cesium. Lots of atoms show this property. And in 2003, first molecular Bose-Einstein condensation is observed. So the beginning is this. There were cooling, experimentally cooling to very low temperatures indeed, 170 nanokelvin, for example, nanokelvins, 10 to the minus 9 Kelvin. Still not zero, you should remember. Extremely important. First, let me ask you why rubidium 87 or 85 are bosons. They should be bosons to show this property, isn't it? Why do you think rubidium 87 is a boson, for example? Can you tell me? Think about it. What should you do to decide? I think you should count the number of fermions you have. If you have an odd number, you have fermion. If you have an even number, you have boson. Huh? For rubidium 87, you have 37 protons, 50 neutrons, and 37 electrons. Those numbers should be equal to get a neutral atom, not charged ion. So the total number is 124, isn't it? So you have a boson. So it is normal that under these extraordinary conditions and dealing with bosonic atoms, they were able to see the condensation. Did you check the picture? Not yet. Check the picture after the lecture. Okay. It is a very interesting phenomenon. Well, sometimes it is called a phase transition, but this is the only phase transition where the phenomenon is happening without the interparticle interactions. We are dealing with an ideal Bose gas, no interactions between particles, but still we have a transition. So it is kind of a phase transition happening in K-space, not in real space. No interactions are needed. The only phenomenon where you have this condensation. Now let me give you another example. Of course, now I'm not going to keep the number of particles fixed like tens of thousands of atoms as it is done in this experiment. Let's keep the number of particles not a constant, okay, a variable. Because when you think about blackbody radiation, it is the gas of photons, and how can you keep the number of photons constant when you have a photonic gas, where you have constant emission or absorption of photons with the walls of the container, okay? So it is like heating a piece of metal with a cavity, where you have radiation in that cavity, you have a blackbody radiation in that sense. So, have you studied blackbody radiation before? Did you understand the phenomenon? Are you sure? I mean, did you get it from first principle conditions, calculations, or did you get it after an assumption about the distribution of frequencies coming out of the heated bodies? Planck was the first guy who did the father of quantum mechanics in some sense, because he came up with the Planck distribution of frequencies. But up to now, I don't think you have done it completely and correctly. You needed an assumption. Okay? Now, it is the statistical mechanics that can give you everything about blackbody radiation without assumptions of such kind. Now, there are two different approaches. One is the Planck collection of harmonic oscillators. The second one is the Bose-Einstein. I'm going to consider the second approach, second point of view, which is originated by Bose and Einstein. It is also an interesting history of physics. The point of view is that consider blackbody radiation as a photon gas, a Bose gas. So this is done, well, let's put the subject as thermodynamics. Of blackbody radiation. Bose did it for the first time in 1924, sending the results to Einstein. Who worked on it a little bit more. The result is the famous Bose-Einstein approach. Let's find the density of states for this gas. What type of boson gas we have for the blackbody radiation or photon gas? It is relativistic, isn't it? Energy is no longer p squared over 2m. What is it? E equals c times p, isn't it? So it is a relativistic gas. Density of states can be written as follows. Energy c times p, or you can also write it as h bar omega, omega being the frequency associated with the specific photon, so that p is h bar omega over c. Well, we can use the form in P in terms of momentum, V over H cubed, D cubed P, isn't it? But here there is a possibility of two transitional transverse modes So we have to multiply our earlier result by 2 because there are two transverse modes for the radiation. We don't have a longitudinal mode here, isn't it? It is not like a sound wave. This is electromagnetic wave. Huh? There are only two transverse modes, 2 times the earlier result in terms of P. Let's write it in terms of P and turn it into energy. Okay? Or h bar omega in terms of frequency. Well, it is V over H cubed, 4 pi P squared d P, isn't it? So we have the density of states in this case in the form V omega squared d omega divided by pi squared c cubed. This is our density of states for this gas. Is that okay? Huh? Well, without the 2, we have the earlier result. V over H cubed times D cubed P. Huh? 4 pi P squared dP. Then I'm turning it into frequency range. So instead of counting states in between with values from P to P plus dP, you are counting now modes from omega to omega plus d omega. Okay? That's counting of states, density of states, number of states in that range. Do you have any questions? No? Okay. That's the density of states. Keep that in mind because we are going to use it when we write the energy and other things. Let's start the calculation. But before that, let's find the distribution function for this gas. It's a boson gas, but what is the actual form of the distribution function? That means average occupation number. Let's find that. Average occupation number is, there is no limit to the number of particles now. We are dealing with bosons, and the total number of particles is not fixed, is not a constant. And as energy, omega s over kBT, beta E minus, there must be ns here too, minus ns times that, total energy divided by kBT, divided by ns from 0 to infinity, e to the minus ns, beta h bar omega s. Okay. You can also write this as minus del alpha ln sum over ns e to the minus alpha ns. Logarithm, isn't it? 1 over the function, derivative of the function with respect to alpha brings down an ns. So this is nothing but 1 over 1 minus e to the minus alpha, e to the minus alpha. So the result is 1 over e to the beta h bar omega s minus 1. H bar omega s over kBT minus 1. Is this okay? That is the occupation, average occupation number distribution function. We know the density of states. We have the distribution function. We can calculate whatever we like. Well, distribution in energy, what is the energy distribution? It's the same thing with frequency. Let's find that out. Instead of assuming a form, let's calculate that. U omega d omega must be h bar over pi squared c cubed omega cubed d omega divided by e to the h bar omega. Beta h bar omega means h bar omega over kBT minus 1. Okay? If you put it into dimensionless form, we can get it in terms of temperature. How can you put it into dimensionless form? Call h bar omega over kBT. X, that's unitless. H bar omega is energy, kBT is energy. So you have a unitless number. So in terms of this, you can write U omega d omega as KB T to the power 4 over pi squared h bar cube h c cube x cube dx divided by e to the x minus 1. So x dependence is here. Let's call this u prime x. If you plot that, you see the distribution as follows. As a function of x, u prime x, it is the Planck's distribution. A little bit back over the maximum is 1.5. Okay. So, what is the total energy of this total energy density in the cavity? So you are having a metallic material. Do you know what happens when you heat the metal? The color changes, isn't it? It starts to glow, reddish, then a little bit whitish at the end. So it goes over to higher frequencies. So energy density, total energy density becomes now if you heat the metal and have a cavity, then of course the metal will emit photons and that cavity will be filled with radiation. That's the collection of photons we are talking about. Total energy density is total energy per unit volume, and it is this ux dx, isn't it? U omega d omega, you can call it ux dx. If you do that, you have the following: kb to the t, kb t to the power 4 pi squared h bar cube c cube integral from 0 to infinity x cubed dx e to the x minus 1. And this thing is a number, an integral. It is written as pi to the 4 divided by 15. This is nothing but the area under the Planck's curve, isn't it? That area. So the result is then pi squared kb to Boltzmann constant to the power 4 divided by 15h bar cube c cube multiplier times t to the 4. Now, if you have a small opening to that cavity, so that photons will go out of the cavity, if you do that, you have to integrate over the forward angle. Probably you know that from the black body radiation problem. And you get the following. frequency distribution of outgoing photons. Small opening in the cavity, so it will result in effusing. So they are going to effuse from the opening. So the quantity you should be interested in, this effusing photons will have the following distribution or dependence on temperature. C squared T to the 4. This is usually written as sigma T to the 4. Did you remember this? Do you remember that? That sigma, these constants are pi squared kb to the 4. Well, this is the value. And when you multiply these numbers and divide, the result is 5, 6, 7, 0, 10 to the minus 8 watts per meter cube for K to the minus 4 Kelvin. We call this Stephan's constant. Did you hear about this? The guy did the experiment in 1879. These are heroes, you have to write that. And that distribution is known as Stefan-Boltzmann law. Stefan-Boltzmann law. Okay. So we didn't do anything. We just applied what we know about our gas, Bose gas. Can we get thermodynamics of this gas? Of course we can. We know the way to do it now. Thermodynamics is going to come from logarithm of the ground canonical partition function. I will show you the way you should do it. See, photon gas then is what we are dealing with. Ln of Q, ground canonical partition function. Number is not constant. When n is not constant, we should always remember this important restriction. N equals constant is a restriction, isn't it, on number of particles. Now we lift that here, minus ln1 minus c to the minus beta e. Everything is coming naturally here. If you replace the sum by an integral, you need density of states in terms of energy, isn't it? So those for this relativistic gas is in terms of energy. Why don't you play with it? 2 times V over H cube, 4 pi P squared dP. So this turns into 8 pi V H cube C cube E squared D. For the classical gas, it was square root of energy, non-relativistic gas, I mean. Huh? For the relativistic, now it is proportional to E squared, not square root of 2, square root of energy. Okay. So, we are almost at the end. With this ln q curly q vt can be written as putting this density of states and turning the sum into an integral. Well, that was also equal to PV kBT. You get the following: 8 pi V 3 H bar cube C cube 1 over kBT 0 to infinity energy cube D divided by e to the E over kBT minus 1. If you put it into unitless form, I have given the value of that unitless integral. Do you remember from the earlier lecture? Was it pi to the 4 divided by 15? Something of that sort. So if you let x equals E over kBT, you get that integral back, pi to the 4 15. You get this to be 8 pi V 3 H bar cube C cube kBT to the 4. Why kBT to the 4? Because we have cube and one more, dE, isn't it? dE can be related to dx, but you have to multiply by kBT. Huh? You don't see it. dx is related to dE over kBT. So dE is kBT dx. There is kBT cube here. You have kBT to the 4. Okay? kBT to the 4. And what do you get for this? Zero to infinity, x cubed dx, e to the x minus 1. This thing was pi to the 4 over 15. So we have explicitly the form. From here, we get 8 pi to the 5 V divided by 45 H bar cube C cube kV T to the power 4. And when you compare this with the energy expression, U, you see that this gives you the following relation. PV, so that gives you PV 1/3 U. Basically, this is it. Before I quit, can you give me the most interesting example, one of the most important examples of blackbody radiation that you know? Heated metals, of course, will fall into this. But what about an important example, blackbody radiation? Background radiation, did you hear about that? 2.7 Kelvin, background radiation. Remnant of Big Bang. That's the most important example, one of the most important example of blackbody radiation. Are you tired today? Are you tired? Did you have enough? Okay, let's discuss some physics.